Well, good morning, everybody. Did I scare everybody off with the field trip announcement? Yeah?
Field trip?
Yeah, field trip today. You're supposed to wear your running shoes.
I got him in my car.
Joey? Yeah? Okay, no. That's all right. You'll be fine.
Don't worry about it.
Let's see. Which lab are we doing tomorrow? 5, because we don't do things in order in physics. Okay. And I think that's it. Test coming up 2 weeks from tomorrow. 2 weeks from tomorrow, right? So, all right. Today, we are going to talk about kinetic energy. We're going to talk about power. That will be the end of chapter 6, and then 7, and then we will roll into chapter 8. I know it feels like I'm kind of like way ahead compared to your homework, right? Okay, but that's on purpose. So we'll start chapter 8 today and learn about potential energy. So we're putting pieces together of that conservation of energy concept that I told you about before. But let's take a look at something that's a little bit familiar maybe, or you might even, dare I say, be happy to see. Oh, old friend. Back when you thought physics was hard, right? Okay. You remember that little innocent piece of you that thought, oh my gosh, kinematics. Yeah, well, you've been into Newton's laws now. Why am I writing this on the screen? Well, I want to, so you should know that this class, I teach this class very differently from the way I was trained to teach it. If you are all physics majors, this class will be taught very differently. But since I know most of you are engineering majors, and there's a smattering of math and chemistry and some biology and stuff in there, I try to be much more applications focused. So you'll see me doing examples that apply to the real world. There's very little of what we do in physics, which is mostly derivation. But sometimes I just can't help myself. And I have to derive something. I have to show you where it comes from. And this is one of those cases. We're going to pull kinetic energy out of this seemingly innocent third equation that we had in our kinematics toolbox. And I feel like sometimes this is like a bit of a magic trick. Right? It's just like, whoa, where'd that come from? So watch as I perform a little bit of a mathematical sleight of hand here. Okay? Let's solve that equation for acceleration. That's going to be a v squared minus a v naught squared. And you know what? I should have said, you don't really need to write down the derivation. We'll get to the punchline, right? And I'll box that answer. That'll be the thing that we're going to apply. And I know I just told most of you just to go to sleep for the next 5 minutes, but you'll want to watch it. You want to. This is how discoveries are made in one sense of that word. Okay, so there I have a way to write acceleration. And if we go to Newton's second law, I'll sort of write it the so-called forwards direction here, right? We know that force, mass, and acceleration are all related to each other. So I can take my acceleration that I found over here and go ahead and kind of throw it in there, right? And I'm gonna multiply both sides by delta x now. Over here. So what do I end up? So this one cancels. And then I end up with a force times a distance equals, it's like a 1/2 m v squared minus a 1/2 m v naught squared. Okay. So I multiplied sort of through with that m. It was a 1/2 on the bottom, kind of pulled it through. And I'm staring at this, and I'm going, wait a second. I know what that is. What's a force times a distance? It's work, isn't it? Right? That's how we defined work. It can be a scary integral, but we won't go there. So this is a work, right? And did we ever talk about the units of work? Did I forget to do that? probably forgot to do that. It's in the book. It's called a joule. Joule. James Prescott Joule. It's a unit. Yeah, we use it all the time. It's energy has the same unit as work. And you'll see that here in a second. Joules are a little bit difficult because, so what's the unit of a force? Newton, and then a unit of distance? So it's a Newton times a meter. We just give it a different name, a joule. You're very unfamiliar with units of energy. Like even in the sort of US system of units, we don't use units of energy very often. I think the closest you get to is maybe on a power bill where you're billed in a kilowatt hour, which I'll talk about later. So they're not all that sort of familiar to you. I had a list at one. Do I still have it in here? Yeah, okay. So like just to give you some like ideas about how big a joule is or how small it is or all that kind of stuff, like turning the page of your notebook, right? Just flipping this page over uses up about a millijoules worth of work or energy. Okay, so that's a very tiny. That's 1/1000th of a joule is that right there. Okay, a car moving at 60 miles per hour, and this would be like a standard sedan type car, has about 800,000 joules of energy. So there's like kind of a big range there, right? And so it's probably very meaningless to you to tell you that your heartbeat takes about a joule's worth of energy. Like it just, we're not familiar with those numbers, so you just kind of have to run with it, right? You know that when you calculate work, you calculate energy, you're going to end up in this unit of a joule, and it's a unit of energy. You're probably, you know what? I know one unit of energy that you're probably more familiar with, and we really can't talk about until Physics 4C. What's that? The calorie, okay? Not the dietary calorie, that's different, okay? But the scientific calorie. Scientific calorie is a unit of energy. It's equivalent to 4.186 joules. I usually just remember 4, right? One scientific calorie, which is 1/1000th of a dietary calorie. So basically, a calorie on a food label, okay, would be 4,200 joules worth of energy, right? So if you're doing a 2,000 calorie day diet, right, you need 2,000 calories to do whatever it is you need to do biologically, then you take that 2,000, you multiply by 4,200, you got the total number of joules you're consuming in a day, okay? So it's a unit of energy, and it's the SI unit. The calorie is not an SI unit technically, okay? It's a special chemistry unit that everybody seems to use. Anyway, it's been sort of semi-adopted into the SI unit system. Back to this. So we got work, okay? And then we have a difference of something over here, don't we? We have a 1/2 MV, what kind of V? Final, minus a 1/2 MV initial. So there's like a final minus an initial thing over here, isn't there? We're going to give that thing a new name, right? We are going to call 1/2 mv squared the kinetic energy. Work and energy are related to each other. They have the same units. Work gets done, and that causes energy to change. Which is why I can write this work as a change in kinetic energy here. This is a relationship that's true, right? Where that change in kinetic energy is a final minus an initial value. I usually write, your book usually writes KE, just to not confuse it with other Ks, right? But this idea, this definition of what kinetic energy is, arises from what we know about work and one of our old friends, the kinematic equations. So what do you need in order to have kinetic energy? We got to have velocity. Something has kinetic energy if it's moving. What's its kinetic energy if it's not moving? 0. This is great, right? None of this weird stuff with acceleration and velocity and getting tricked about that, right? If it's moving, it's got kinetic energy. If it doesn't, does it ever have negative kinetic energy? No, it's a squared value, right? Okay, so it's energy is energy regardless of what direction it's going, right? You got to have mass, right? And that squared thing there, if you're going, I don't know, 10 meters per second and you double your speed to 20 meters per second, what happens to your kinetic energy? Exponential is a strong word there. Okay, you go from V to like 2V, right? That was a really bad 2. 2V, right? Then your 1/2 mv squared becomes a 1/2 m 2v squared. And when you square that 2v, what happens to the 2? Becomes a 4, right? This is 1/2 m with a 4 times a v squared, which is the same as 4 times 1/2 mv squared. And what's 1/2 mv squared? It's what I started with, right? So notice that by doubling the speed, we have increased the amount of kinetic energy, not twice, not 3 times, but how much? 4 times. So what does that mean for the work that you have to do to slow the car down? 4 times the amount of work. That means your brakes have to do 4 times the amount of work to bring your car to a stop. Right? So, that's kind of interesting. So it's a change in kinetic energy, right? If we're going from 60 miles an hour to 0, the final kinetic energy is what? 0 comes to a stop, right? And the initial is not 0, right? So we have 0 minus a number. What kind of number are we going to get? That's a negative number. What does negative work mean? That the force that was applied, the friction, is opposite the direction that the car was going. So these things work out to be consistent with everything we learned about like positive and negative work last time. And so, that without really having to check any kind of vector direction, it just kind of comes out automatically. What happens if you go 3 times the speed? How much does the kinetic energy change? By 9, right? You got to square that factor by which things change. Okay? So kinetic energy, kind of a nice, straightforward idea here, right? Something's moving, it's got kinetic energy. And to get kinetic energy, you have to do work. Like, how do you speed your car up? Right? Push the gas pedal. That causes the motor and everything, and the friction between the tires and the road, and it speeds it up, right? Work gets done, force gets applied in the direction you want to go, and that's a positive change in kinetic energy. Yeah, delta KE. I'm not being very consistent with my symbols. I should be fired. Whoops. KE. There we go. All right. So let's now, this is important, slightly tangent. We're going to do it here because it makes more sense to do it here than to do it later. What's power? Money. Right? Those that have money have all the power, right? No, that's not what power is.
It's another one of those, like, you can't really define it like the mass.
No, actually this one we can define. This one we can define. But we tend to think of power, not in terms of its scientific definition, but sort of how it works maybe in our society, right? I have power over you, I'm your teacher, I control your life, right? All that kind of stuff, right? Your boss has power over you, your parents have power, whatever, okay? Power does have a very specific definition in science, and I know that comes as a great shock to you, right? Okay? But power is equal to work divided by time. And you'll often see physicists say, well, it's energy divided by time. It's because work and energy have the same units. Okay? They are slightly different ideas, right? Work is force applied over a distance. Energy is what you get when you do work, but they share the same unit. But I do want to just take a slight sideways moment here to help out my brothers and sisters in the humanities, okay? We need to give them some reason to exist, right? So we're going to teach across the curriculum here. They encourage me to link this stuff to the other stuff you're supposed to be learning in your college career. And so I pulled out some quotes. I know. Okay. Does anybody know who, he's got a kind of obscure kind of guy. Thomas Jefferson?
Never heard of him.
Never heard of him, yeah. If you must be from Texas. You guys know about that, right? It might have been right around the time you were being born. Texas tried to remove all references to Thomas Jefferson from the history textbooks in the Texas state curriculum. Thomas Jefferson, John Adams, Quincy Adams, John, whatever his name was, not Hancock. Several of the founding fathers. And do you know the reason that they gave? This is not a direct quote, but it's a paraphrase, but it's really close. Quote, "These individuals do not enshrine the values of our American democracy." Unquote. Yes! That's Texas for you. Anyway, Thomas Jefferson. "I hope our wisdom will grow with our power and teach us that the less we use our power, the greater it will be." Is that like a lesson we could learn today? The restraint of power makes us more powerful. Abraham Lincoln? He didn't do anything, right? Now, of course, several of these quotes are, Lincoln's in particular here is going to be phrased in the, the male context, using the word man, not just to mean men, but everybody. I won't change his words and modernize it, but we know it applies to everybody. "Nearly all men can stand adversity, but if you want to test a man's character, give him power." It's kind of a deep cut, isn't it? Yeah. All right. This last one, I don't need to read this one I've got. This one is seared on my soul. Now, unfortunately, I can't do the voice. Okay, so you're just going to have to provide the voice for yourself. Okay? But let's see if you can name the person that says this quote. "The power to destroy a planet is insignificant when compared with the power of the Force." Who? Darth Vader! Right? Rest in peace. James Earl Jones passed away last week. The voice of Darth Vader. Oh, yeah. Oh, Darth Vader. Right? He was the nightmare of this 6-year-old's nightmares. Right? Like when he came walking down the steps in the Return of the Jedi, not Return of the Jedi, The Empire Strikes Back, I peed my pants right there in the theater. I was convinced Darth Vader was coming after me. Okay, so now that your horizons have been broadened and you understand a bigger context of power, let's get back to the real definition. Work. So what are the units here? This has to be a joule per second, right? That has a different name. And it has to do with light bulbs. Watts. This is a watt. So you've actually run into this idea before, right? You're probably familiar that light bulbs have watts or use wattage. Like if you have a 100 watt light bulb versus a 10 watt light bulb, you kind of have an idea of which one's going to be brighter, which one's going to take more energy to run, okay? That kind of stuff. So watts is somewhat familiar. You're probably, maybe not light bulbs, maybe more nowadays it would be like the wattage that your phone charger delivers, right? Because if you have a 5-watt charger versus a 20-watt charger, which one's going to charge your phone faster? The 20 watts, right? Okay. But what's that trying to say? It's trying to say that 20 joules of electrical energy every second is being delivered to your phone. A phone that charges wirelessly, right? You put it on the charging pad or something instead of plugging it in. Those are limited between 5 and 7 watts most of the time. There's newer versions that can do 20 watts, 15 to 20 watts. But like you can get 100 watts, 140 watts going into a phone or a laptop from a wire, right? So obviously there's more energy per time that can be delivered via the copper than through the magnetic fields of the charging pads. So you have sort of this idea, right, that watts and, right? But what does that have to do with like physical? That's electricity, Mr. Bailey. You're teaching us physics 4B. That's no fair. I signed up for physics 4A. When we refer to power outside of electricity, what units do we use? Like, what's the power of a car's engine measured in? Okay. All right, horsepower. First question. What kind of horse? Right? Because I've worked with a lot of different horses in my life. I did work with horses for a long time as a child, a teenager. It's a summer job. But like I've ridden Icelandic ponies. They're basically like just kind of large dogs. Like literally, if you put your feet down, you probably touch the ground while you're on one. Okay, that's even me, and I'm short, right? To Belgians, those of you who don't know horses, I'm basically describing a elephant that's wearing a horse costume. Okay, like just huge, and everything in between: Mustangs, quarter horses, Spanish, like all different kinds, right? And so there's a big difference between what a little Icelandic pony can do and those big Belgians. Like I don't know if you've seen the beer commercials with the horses, right? Is that Budweiser? Do they still do those Clydesdale horses? Really big horses pulling the thing. Basically the same horse. It's just Clydesdales are show-offs in Boston. Anyway. Horsepower. What's a horsepower? No, well, that's more. So there is a definition. 550 feet times pounds per second. Wait a second. Yeah, what is it? What's a foot-pound? Somebody's going to say torque, and that is true. That is a unit of torque. But back up. A foot is a distance, and a pound is a force. What is that? It's work, right? Turns out work and torque have the same units, okay? More on that later when we get to torques. So that's a work. That's like an energy. It's a work energy thing sitting on top, right? Divided by time. So that is a power unit, is it not? Where'd the 550 come from?
Probably a horse or something.
Okay, so back in the day, this was developed around the time that like steam engines were being developed, and they wanted a way to sort of compare and quantify the different designs with each other. And a horsepower was defined because a horse could either pull or more correctly lift a 550-pound weight through a distance of 1 foot in 1 second. So you attach a horse to a rope goes over a pulley, attaches to a big weight, 550 pounds, okay? And then you tell the horse, go. And so the horse goes, and in 1 second, pulling on that rope, it can lift that weight through a distance of 1 foot, right? And that was defined as like the standard horsepower, right? And then if you had 2 horsepower, 3 horsepower, you could then kind of compare what's going on. And they could kind of do the same thing with their steam engines, right? You could see how much force was applied in time and get this idea. It's like all English system of units, it's an awkward unit. If you want a conversion from horsepowers to watts, it's 746 watts. Okay? But we tend to, especially like with cars, engines, things that aren't electronic, we kind of go to like horsepower to talk about this because power, right, is work. Work usually ends up causing a change in kinetic energy somehow, right? And that's why we kind of go to it. There's other things about power that are kind of interesting here. One of them is we can like, so technically, you notice I haven't really kind of drawn a box around this yet. It's changes. I probably shouldn't do it that way. Another way to write power is a change in energy over time, because work is equal to changes in energy. We'll get to that later. So if this is a change in energy or a change in or work is being done, that means I've got a force times a distance, like final, minus a force times a distance initial over time. We'll keep the force the same. How do I write a difference in distance? I could just say delta x, right? Okay. And so we got over delta time. What's a delta x over a delta time? That's a velocity, isn't it? So this ends up being F times a velocity. Power is a scalar. It's not a vector. But force is a vector. And so is velocity. So what kind of multiplication is this? The dot product again. Okay. So another way to find power is to know how much force is being required to keep something going at a constant speed. You can find your power there. Or if you know the power output, say, of an airplane engine, and you know how fast that airplane engine is going, you can figure out the thrust of that engine, find the force, right? So lots of different ways to kind of use these relationships that are sitting here.
What's thrust? Is thrust a type of unit or?
It's force. That's you pushing something. It's another force. Yeah, it's the push that causes an object to go somewhere. So rockets have thrust that way. Airplanes have thrust pointed that way. So lift is different. Lift is that way. But anyway, yeah, just different engineering terms for all forces. Physicists would say they're all forces. I was trying to be engineering, maybe it failed. Okay, so the big question I think we need to answer today is this. Are human beings capable of a horsepower? Well, we know cars are, right? But human beings. I submit that, we have a bunch of normal human beings in here, okay? Okay, all right. Can a human being lift 550 pounds 1 foot in 1 second? Yes. Well, not this human being. Yes. No. Okay, right? Not going to happen. But can we game the system? Instead of 550 pounds through 1 foot in 1 second, what would happen if I did 225 pounds through 2 feet in 1 second? That's the same value, isn't it? Or 112.5 pounds through a distance of 4 feet in 1 second. Because 4 times 112 is still 550, isn't it? So, do you see how we can kind of game the system here? Okay. So, we're going to take a field trip. Okay, I need 44 volunteers. Okay? Need 44 volunteers, right? You're going to be split up into different groups here. Okay? So pay attention. If you don't want to be one of the first 9 volunteers, then you will default to a volunteer role. Okay? But this is what we're going to do. We're going to go measure the horsepower of human beings. Okay? And the way we're going to do it is, quite frankly, the gym is not open for us right now, so we can't go lift weights. But we're going to lift the weight that everybody is built with. And how are we going to lift it? Up the stairs. Okay? So what we're going to do is we're going to take 3 volunteers, okay? And we're going to run them up the stairs. 4. We'll do 4 volunteers. 4 volunteers up the stairs, okay? Right? So what work is this person doing? What are they working against when they go up the stairs? Gravity, right? In other words, they have their weight, don't they? Okay? And what distance matters? It's the vertical distance that matters. The horizontal, right? Because gravity and dot product 0, right? So we only need to know the vertical distance that the person goes through. So if we can measure the vertical height of the stairs and we know the person's weight, what's the last thing we need to calculate their power? Time. How long it takes for them to get up the flight of stairs. So let's see. Power, work over time. That's force times distance over time. The force is going to be their weight. Okay? The distance will be the height of the stairs. And then time. Now, we want to do horsepowers, right? So we better work in the stupid unit system. So weight. What unit do we want the weight to be in? We'll do the weight in pounds. The height of the stairs, we'll do that in feet. Okay. Time is the same. Okay. So that'll give us a foot-pound per second. Is that a horsepower? No. We have to do a conversion factor, right? And so the conversion factor would be on the bottom 550 foot-pounds per second in 1 horsepower. What?
Foot-pounds a second.
Pound-feet per second? I don't know, whatever. Okay, right? But my units all canceled and I ended up with horsepower, right? So a person's power calculation is going to be their weight times the height of the stairs divided by their time, with a 550 also down there in the denominator. All right? So that's the calculation we're going to do. All right. So I need, this is the list of volunteers. Don't raise your hand all at the same time. I need 4 people who are our guinea pigs, who will be the people running up the stairs. Okay? As a preference, I would like gender balance there, but that is not required. I need 3 people to measure the height of the stairs. We'll give you a tool, okay? But 3 people will be measuring the height of the stairs. And then I need 3 people who will act as timekeepers to measure the times of people going up the stairs, okay? Anybody else is a data taker. You will bring phone, paper, pencil, blood on parchment, I don't care, something, okay, to record the data that we are going to go take on the back stairs back here, okay? But we're going to go on a field trip through the dungeon that is the back of the middle of this building. You're going to see some things. No, you can't touch anything. Okay? But we're going to go this way. I will lock the doors here so that you can leave your stuff in here and nobody will mess with it, right? I'll lock those doors. All right. Who would like to measure the height of the stairs? You guys always, it's always the opposite sides of the room. Okay, who's my other measuring the height of the stairs? One more person. Oh, thank you. Okay. All right, who will take time? All right, good. You guys had mercy on me over here. Okay. All right, and who is willing to have their horsepower measured? Now, before you all raise your hands, you do have to disclose your weight in public. You were good with that? Okay, so we'll do Ray and Alette. Did I spell it right, Alette? Ah! There's one L, isn't there?
Yeah.
Darn it. Like that. Right, Alette? Got it right. Okay. Liam, there's too many of you. Okay, that's what we'll do. Gentlemen, we'll get you next time. You'll be all right. You can do it at home. Okay. Those of you that are taking notes, okay? Get these names down, okay? We'll do the weights later. Let's go out and get the times. Okay. So let's see here. I gotta lock the doors. Okay. You're locked in now. Gotcha. All right. The people on YouTube are going to wonder why there's like a 15-minute blank spot in the recording. That's all right. Let me prepare the way. Get ready. I'm taking students back here, so I'm going to close this door. All right, you're all coming out this door right here. Buddy system, all that kind of thing. You ready? Okay, let's go. Follow me. Follow me. No touching. Don't let Simon touch you. Okay, I'm salmon swimming upstream here. Salmon, salmon, salmon. Salmon swimming upstream, swimming upstream, swimming upstream. Yeah, they're behaving?
Yeah.
Okay. Better watch Eduardo, though. Keep an eye on him.
Is it not touch, right?
Yeah, yeah, yeah.
Oh, violated the rule.
Look at all these excited students. Actual field trip in physics. Who knew?
I mean, I was excited when I went to the staircase.
Huh? All right. Yeah, what?
Do you know how long we'll be out there for? Because I gotta go in 10 to 20 minutes.
We'll be out there for at least 10 minutes.
Okay.
You good? Okay. But probably not 15. All right. All right, people measuring the height of the stairs. This is what we're going to do, okay? We're going to all the runners on the middle thing down there.
I'm going now.
Good, good. And where are my timers? Need timers. I get. Oh, here we go. Who wants to be in charge?
I'll be in charge.
Izzy? Okay, Izzy's going to be in charge.
What
So
am I in charge of?
you're you are the ready, set, go person. Okay?
Oh.
So what we're going to do is we're going to do what's called a kind of a quick or a bad average. All three of you are going to have timers, right? And so as soon as Izzy says go, you start your you guys know how to work these? Okay, good. All right, you clear them out. Okay. So you ready, set, go from Izzy. You're going to start your stopwatch. And then let's just agree Imagine there's like an invisible beam right here or something. Once any part of their body passes that plane, you're going to hit stop. And then let's say you get 2 seconds, you get 2.4, and you get 2.7. Just take the middle number. Okay. Out of the 3 numbers, whichever number's in the middle, if 2 of them are the same, just take that one, right? But you're just going to take the middle number and we'll report that one. Does that make sense? Izzy, you'll call out that number when you guys figured out what it is? Okay. All right, data takers, you ready? The rod. Or do you want to do 7.1? You got all engineers, what do you want? 7.2? Just round it up. 7.2, 7.2 feet. Quick time. Oh no, don't do that. All right. All right. Here are the rules. Mostly you guys need to hear. Here are the rules. Rules are you are not allowed to hurt yourself. It's rule number 1. Okay? Rule number 2, you can use any part of the stairs you want. So you can use handrails, you can skip steps. It's just you got to get up there, right? Any way you want, okay? Rule number 3, you're not allowed to hurt yourself. Do we understand rules 1 and 2 and 3? Okay, you guys ready? Okay, Ray's gonna go first. Yeah, okay, so Ray is up.
No, 2.06.
2.06. 2.06 for Ray, laying down an early. Smooth.
2.32.
2.32.
2.32. 2.32 for Liam. Wow. That happened in 4 steps.
No, guys, I can't do better than that.
It's not better or worse. It just is.
1.84.
1.84? Loving it, loving it. 2.94. 2.94. All right. Mr. Balogh's turn. All right, 1.2 seconds. Let's go. Right back inside. So you took down my. It was a block.
You needed that?
Yeah, it was directing students. Don't let them go in there.
1.27?
1.86 was my time. 0.86. 0.86.
Yeah, you guys didn't see it. He was like the flash. Mr. Balogh, I'll be honest, I blinked and then you were up there.
It's true, right? Like 0.3 seconds, wasn't it? Oh, I need this. Sorry, not doing my job here. Did we lose anybody? No.
Hey, good job.
Sarpani, you got everybody? You keep track? Okay, good.
Usually there's
Yeah, thank you.
one casualty.
Yeah, we usually lose like 6 or 7 people.
Did you win today?
We're going to find out.
Oh, you're going to find
Yeah.
out.
Amazingly, my time was like 0.1 seconds up the stairs.
really?
Oh, yeah.
He did it in like 2 steps. It was crazy.
Yeah, yeah. It was
I couldn't see him. He was just
Oh,
one
thank you.
second there, next second there.
we should have timed you.
I saw
All right, where'd my other Ian? Where'd the? Let's see. Izzy, did you do anything to my phone while you had it? Okay. Stopwatches. Where? Oh, thank you. Okay. What do we got here? Let's see. Since we're going to calculate weight, so we know the height of the stairs. What did we say? 7.2. Okay. Really, the time. So a person's weight and we have automatic in this calculation is going to be a 7.2 over a 550. What's that number? What's 7.2 divided by 550? Everybody needs their calculators out. 0.01? 0.013. So that's like the common factor. And then we're going to take their weight and divide by their time, multiply by 0.013. Does that make sense? Just making it easy for everybody to calculate stuff out here. Okay, so Ray, what's your weight?
215 pounds.
So 215, and what, Alette? 100. And Liam?
200.
And Omari? 167. And Mr. Balogh, 4,873 pounds. All right, so time, what was Ray's time? 2.06. I thought it was, yeah. 2.06. Is there some discrepancy in the data? Alette, what was Alette's time? 9.4. Liam's? 3.2. Amari's? 1.84. And Mr. Balogh was 0.077. All right. So this is what you're going to do. You are going to turn to at least 3 neighbors, tell them the one that you are calculating, and then the people around you have to calculate a different one. Does that make sense? So just the people around you, make sure you're not all doing the same one.
He's a Lamborghini up there. That's what he's running as.
All right, so does anybody have Ray's yet? 1.36?
No, that doesn't sound right.
I got yours.
What was Ray's? 1.3? 6? 1 point. What? What? What about Alette?
0.4 or 5.
0.5? Oh, decent. Liam?
1.12.
1.12? You guys been training or something? Omari? 1.18? And Mr. Balogh? Yeah. All right. 180 pounds. And then, what was my time? It was 2.4? We'll do 2.4. I really, we should really write these things down. That's what we should do.
0.975.
Is that?
I have 1.086.
I have 0.98. 2.4 was my time. I was a little slow today, so 0.98. Okay, typically I get over 1 horsepower, but I'm old today. All right. Are humans capable of horsepower? Yes. Yeah. Is Alette capable of horsepower?
No.
Yes. Yes. The answer is yes, right? Now, why was hers lower than everybody else's? Less weight. So notice how in this calculation, the more weight you're working against more stuff, right? Okay. And then also her time was the longest time, wasn't it? So those two things together lowered this down. So can we change Alette's weight?
Yeah, hopefully.
Can make her carry something. Don't eat a lot. Okay. And then lower the time. That's a matter of training, right? Okay. Now Alette did hit every step, being as careful as possible.
I knew I was going to break rule 1 and 3.
Right. We didn't want to break rule 1 and 3, so she did just right, right? But I have no doubt that Alette could cross a horsepower. So what's the difference between you and a horse? Beyond the obvious anatomical differences. How long can a human sustain a horsepower? Not long, right? It's not long at all. Marathon runners output less than a horsepower continuously, but they do it for like 3 hours, right? Okay. Whereas a sprinter will go beyond a horsepower, but they'll only do it in 100 meters, right? So humans can do it, but just can't do it for very long, right? A horse. How long could a horse do a horsepower? Like all day. You give that horse water and some oats, and it's like, okay, let's go. Right? Yeah. So while the instantaneous power output, right, we can exceed it over long periods of time, we did not evolve to put out lots of power. Okay? We evolved to be able to get away from all the lions and things that wanted to eat us, right, in the savannah. So we evolved to be long distance runners and not really sprinters. Although we can do a decent sprint. It's just not great. I'm in trouble. I promised myself that if I ever get under a horsepower, I need to start, retirement time. Yeah. I turned 50 this year.
Don't look a day over 20.
But if we round up to 1 sig fig, yeah, it's 1, right? No, I woke up this morning knowing that I was not going to get a horsepower because my back is on fire. But I'll do anything for you guys. So, all right, that was the end of chapter whatever we were in. Thank you. I'm glad somebody knows what number we're on. I got to reset all my recordings here. All right. So let's go to chapter 8. Where is it? There it is. Chapter 8, like I said, 7 and 8 should really be the same thing because What we're going to do now is we're going to talk about potential energy. And potential energy is going to take several different forms in this class and in 4B and 4C. We know kinetic energy is the energy associated with motion. Potential energy is the energy associated with like a position or a state of something. For example, like whether or not a spring is compressed or stretched, it's storing potential energy. There could be potential energy in chemical bonds, so on and so forth. What we're going to talk about in chapter 8 is gravitational potential energy. The potential something has, right, because of where it is with respect to the Earth, right? So if I take this ball and I just hold it here, does it have kinetic energy? No. But if I let go, is it going to get kinetic energy? Yep. Yes. Where did it get the kinetic energy from? Potential energy. Provided by gravity, right? Gravity was the force that was doing... Wait, so gravity does work on the ball? Which way was the force? Down. Okay. Which way was the displacement? Down. Positive or negative work? That's positive work. Gravity did positive work on the ball, right, as it fell, okay? That work created a change in kinetic energy, didn't it? We just outlined, right? Work causes changes in kinetic energy. It went from 0 to something, right? So all of that's consistent with what we know about energy. So let's calculate the work that gravity did. The work that gravity did is equal to the force that gravity applies times however far the object goes, right? Vertically. Does horizontally matter here? No, because the force is straight down. Okay, so what is the force of gravity? It's the weight, which is what? mg. And then the distance is y, right? Where, like, this distance is y. Sometimes, well, quite often referred to as the height. Even though it's not going up, it might be going down, right? So that's the work that gravity did. That work caused a change in something. Isn't there like an initial y and a final y? It's here and then it's there. If we say 0 is the floor, then what's the final y? 0, right? What's the initial y? Not 0, but it's a number, right? And the change in y, positive or negative? It went down, didn't it? 0 minus our initial thing is a negative number, but it went down. Totally consistent with what we did in kinematics. So it started with potential energy, and it ends with how much? If we name this the potential energy gravitational is equal to m times g times y, then the potential energy is 0 wherever we put 0. Because the 0 height will be the position of 0 potential energy. So we know that gravity did positive work on the ball as it went down, right? But the change in gravitational potential energy, positive or negative? Let's put some numbers in to help you out. I'm going to make numbers up, okay? Let's say the ball has 10 joules of potential energy right here, okay? How much is it going to have on the floor? 0. We'll call floor 0, so it has 0 potential energy. It has 10 here, right? Then what is the change in gravitational potential energy? Delta PE, right? What's the final? PE final minus PE initial. So the final is 0, and the initial was positive 10, which means I have a change. Negative? What can we say about the potential energy? Did the ball gain or lose potential energy? It loses it, right? But what does it lose it to? Kinetic. It's transferring into kinetic, right? Okay? But the work that gravity did, positive or negative? It's positive work, right? We just said that. So that means that work is equal to the opposite change of potential energy. Work is equal to a positive change in kinetic energy. Is that still true? Work was positive, and is the kinetic energy change, delta K, is it positive or negative? Starts at 0, becomes some speed. That's positive, right? So that's consistent. But we're going to take energy away from potential energy for that work to take place, for that kinetic energy to happen. That's conservation of energy. We're changing forms around, and we got to be slightly careful with our directions, but as you'll see here in a second, we're going to fix that, so to speak. But there's a bigger problem, and it's this. We're allowed to pick 0 wherever we want, right?
Yes.
What if the table's 0? And now I hold the ball halfway above the table on the floor, right? Okay, so the table's in between, right? So now it doesn't have 10 anymore, does it? It has 5. What's the change in potential energy going to be if it goes to the floor? This is 5. This is 0, because I changed where 0 was. -5 down here on the floor? So if this was 10 and this was 0 to start off with, right? Then that delta potential energy is 0 minus 10, isn't it? Which gives us a minus 10. Okay, now I'm saying this is 5, right? Where the 0 is in between. And if we are below 0, our distance and our energy and everything, right? mgy, it's a negative y now, isn't it? Because we're below our 0, we're on the negative y side of the axis, so this would be -5, wouldn't it? So what's our change in potential energy now? -5 minus, what's our initial? +5. Still -10? What if I call the top point 0? What would the floor then be? -10. What's our change in gravitational potential energy? -10 minus 0, still -10. What doesn't change no matter where we put 0? The potential energy changes. The change in gravitational potential energy doesn't change, regardless of where we put 0. So if potential energy depends on where we put 0, that means that we maybe have to be kind of clever about what we do there, right? But if the change in potential energy doesn't care, then we're free, as long as we think about changes and not what the actual potential energy is. We're actually going to do both. But I wanted to point out that you're free to pick where 0 is, and there's some pretty clever places to pick it, and I'll teach you about all those things. But really, it doesn't matter. You make a choice, and if you're consistent with your choice, the change in gravitational potential energy will always be the same. Can you put 0 on the moon and have it still work?
Yeah.
Yes. Okay? Because we're going to mostly talk about the change in potential energy and not what the actual potential energy is at any given point. All right. So now that we've basically got all the parts in place, right? We are going to tackle how you use conservation of energy. All these ideas of work, kinetic energy, potential energy, to figure out what's going on in any situation. And it's going to be a little bit magic again. I don't like using that word because really it's just science. We're finally going to be able to do things like air friction. Up to this point, we've been kind of like, yeah, it's physics land. All right. So what are we going to do? We're going to fall back, like everything we do, right, has this 4-step process of the visualize, strategize, do it, check it. Now, of course, details change a little bit, right, with respect to what we're kind of doing in those steps. And it says draw a picture. Now, is that a free body diagram? Can be. Sometimes it's useful to see what forces are acting, okay? But not like absolutely required like it is in Newton's second law. Like in Newton's second law, if you don't have a free body diagram, good luck figuring out the correct equations for Newton's second law, right? But with energy, the picture is more just a way to categorize information. You can even make a list if you wanted to. But the picture does help, especially when you're trying to pick where 0 needs to be. Okay? And notice we're gonna do 3 things here. We've got like, so if we skip down to here, okay? This is our conservation of energy statement. I think I gave that to you before I started chapter 7, right? And there was this work other that I kept alluding to. Conservation of energy demands that whatever we start with, we end with, but we make allowance for energy inputs that, or detractions that we can't, like it's not, if it's not gravity and it's not kinetic energy, then we need some way to deal with it. And that's what the work other term is going to be there for, okay? But in order to apply this, we need to have some point in the motion, in the setup, in the situation that we're calling the initial point. It's a singular spot or condition. And then we need a final point, spot, or condition. And everything that happens in between, conservation of energy doesn't care about. Not only does it not, well, it does care about it, it can deal with it. It's really quite astounding. We just have to compare 2 points. For example, a roller coaster, right? We want to know how fast the roller coaster is going 3 hills down the roller coaster. We take the initial hill, the one that they pull up on, right? Okay. Take the energy there. Then we can compare the energy it's supposed to have at the lower hill, which should be the same energy, right? Conservation of energy. And we can find out how fast it's going. We don't need to know how many hills it went through to figure that out.
So why in the potential energy that the curved one is faster than the straight? Because
Speed depends on a lot of different things in a roller coaster. So I'm not sure I can answer your question.
two same points, but they go in instruments like two balls. One is curved and another one is a straight line.
Uh-huh.
One is faster.
They'll have the same speed at the end if they're at the same height. Ignoring friction on the track. Yeah. You might say that it feels faster on the curved one, but that's different. It's a good question. How many equations do we have? One. This is like the one toolbox challenge, right? Like physics. You get one equation. Now, is that equation going to blow up into bigger things? You now know, right? Never trust a single equation, okay, right? It's going to blow up. So this is an equation sort of generator, so to speak, right? But having said that, it's not as bad as Newton's second law. Let's do a real quick example that we already know the answer for. Free fall. Okay? We've done free fall before, right? So what is free fall? Let's find out. So back in chapter 2, really, okay? We had a ball, and it started with an initial speed of 0, and then it fell down through a delta y, right? And so if we wanted to find out, let's find the final speed. Right? We'll find the final speed here if all we know is delta y. So we don't know time, right? So what equation do we use? Third one, right? And we get the square root, and if it starts with 0 speed, that's a 0. This is 2 times g times my y, right? How far it fell, okay? And you can argue about negative signs, but like if I just use 9.8 and then just use the height, it would work out, right? Because it's negative 9.8 and it's a negative delta y. Done. Okay, so that was a real quick version. How would we do this with energy? With energy, we kind of do the same picture, right? We got the ball. We know its initial speed is 0. We know it's going to fall through a height y, and it's going to have some speed down here. We want to come in and choose an initial and final point. Choose spots where you know something and where you want to find something. So what's a spot that we know something in this problem? The initial, right? So we're going to say that this spot, the initial point up here, is our initial spot. And then for final, we'll go down here because it's where we want to find something. Okay? The third thing we have to choose is our 0 point for gravitational potential energy. You can choose it anywhere, but in terms of easy places to pick, my personal rule of thumb, this is not a hard and fast rule, but my personal rule of thumb for this is pick the lowest point in the problem. That may not even be an initial and final point. It just could be a different point, right? But wherever the lowest point that an object gets to in a problem, that's where you should put 0. So that being the case, I'll put 0 down here at the bottom, which is also the final point. I do work other plus energy initial equals energy final. To answer the work other question, and I'll do more of this next week, you ask yourself, is there anything besides gravity? Any forces that are being applied besides gravity in this situation? No. If there were other forces like air friction or rockets or whatever, okay, that would be work other. I'll show you how to deal with that. But for this problem, we don't have any work other. It's just gravity doing its thing. All right, and then you ask yourself, what kind of energy does it have to begin with? This can be 2 kinds. What are the 2 kinds it can have? Kinetic or potential, right? So what does it have up there? Is it moving up there? No. I'll write down kinetic energy initial, and then I'll cross it out for 0. Plus potential, does it have potential energy initial? Yeah, it's not at its 0 point, right? So we don't cross that one. Now, does it have kinetic energy right before it hits the floor? Yes. Does it have potential energy at the floor? No. So we'll 0 that one out. Potential energy is mg y. I like h better. And then kinetic energy is what? 1/2 mv squared. Solve for v. M's cancel. Multiply by 2. Take a square root. And look what you get. I know you're looking at it going, Mr. Balogh, there's more blue writing than there is black writing. Well, you've been through the kinematics version a lot of times now, right? Seems natural. This is new. This doesn't seem natural. But what would have happened if we had air friction over here? We can't use little g. And our acceleration is no longer constant. If the acceleration is no longer constant, we have to invent a new toolbox to handle that changing acceleration, which means that we need integrals. And this turns into a big calculus problem. In fact, it turns into a differential equations problem very quickly. Okay? Over here, how do we handle air friction? If it's not gravity, where does it go? Force times the distance. I'll show you, not the differential equations part, but I'll show you how to handle work other as we move into next week. I will see you tomorrow for lab number 5.